Good evening, guys. I welcome you to the day 12 of the training uh, on the FPGA development. Today, we are going to discuss about Verilog HDL elements, how to write Verilog HDL according to the operators or the data types. What are the key elements available in the HDL? For any language, we will be having some syntax or some rules and conditions that we need to follow to make it better understanding. In human language itself, we have verbs, we have grammar, and we also have some words to follow on, which are basically understandable to the other person. So in the same way, when we are communicating with the machine, we will be discussing to the machine with some set of protocols or some set of syntax without any errors, and that way machine can interpret the script that you have written and it can turn it into the machine understandable code and then operates on the machine. So let us go to the today's agenda. Today's to-do is about Verilog HDL language constraints, how this language is constructed, and what are the keywords, data types, integers, and syntax that we need to focus on. Mainly memory addressing and array declaration, that we will be showing you how this memory element and arrays are understood in the machine language, and in the hardware description language how do we create arrays of memory. So also the next thing is macros in the Verilog HDL. Macros are nothing but some predefined functions which will be executed at the time of compilation. So we will also be discussing about some operators as well with the data types and all. So let us start our lecture. First thing, what does Verilog HDL have? That's what this question is. Attributes are nothing but elements present in the HDL, or the properties of HDL, you can call it as. So what are the attributes you should remember? First, Verilog HDL is very case sensitive. You should be declaring only in lowercase or in the uppercase. You should be aware of the same terminologies that you use in the beginning of the code and you are using in the end of the project as well. So if you change the names from one Verilog HDL file to another Verilog HDL file on the same module, it will be a difficult task you to debug in the error stage, or it will be difficult for the machine to understand all the modules are interconnected or not. So it will be a chaos again. So the second step is number specification. Yes, Verilog HDL has very much sensitivity in number specifications as well. Whether you are giving the input in binary or hexadecimal or in the decimal, you need to be mentioning in this way. So you can see binary representation, decimal representation, and hexadecimal representation will be looked into this kind of structure. And for this, the first element is known as before the highlighter, this before the tick mark, it is called size of the element, size of the number that you are specifying, size of the bits, for example size of the data, and then radix you need to mention whether it is a binary number or decimal number or hexadecimal number, and what is the value you need to specify. That value should be 1001 and 9 and f is 15, 9 is decimal 9, and 9 can be written in binary in terms of 1001. So in this way you need to specify number, and in this lecture we will be seeing other attributes as well. So let us go to the next thing. And Verilog HDL attributes also consist of commenting. How do we comment? So as we have seen in the yesterday's lecture or day before yesterday's lecture, we can see the comments that if you are commenting a single line, right, you can add these slash marks, and these slashes if you add two, the script that you have written afterwards will be commented. And if you want to comment a para of lines, group of lines, you can start backslash star and para, that entire lines of code, and then star mark and this backslash. Why do we use commenting? It is a best practice as an engineer. Today's tip for an engineer to develop a script is a skill, and make it understandable to the entire team or entire project for year long of information. When you search for the code after 4 years or 5 years and you reusing that code for any another project now, you need to be so specific that why did you use this kind of operator or this kind of function, and how did you develop this function, where did you derive the inputs for this function, what is this line of code is responsible for. I repeat guys, you are commenting to define or to let know other persons or any other project teams to understand what type of code and why did you write that code in that project. So it is a responsibility as an engineer to comment on specific things of the entire code. So commenting is the best practice, and you have to be checking with your team manager whether to give some comments on the code or whether to leave the comments. Most of the time in the industry, people will be asking about the codes with comments. That shows that okay, you are very clear in writing these things, and these comments will help other team members to understand your way of coding and way of developing the hardware. So person to person, the hardware description language or coding style differs in their own ways, but when coming to a team project, right, it should be understandable to everyone. So, and if we comment, sometimes we will be getting stuck at some error, or when we are debugging the code in some particular lines, we may not be knowing how did this operator has been occurring. And then at that time, if we would have commented earlier, we will be checking, okay, this line of code has this error due to the comment. I mean, due to the comment, I can understand, okay, this line has this kind of error and I can rectify with relating to the nearby line of codes. So that is the importance of comment. And space between characters is another attribute. Like for any assignment, assign space, register some equal to, or a equal to c plus b. I'll show it in the next lines of code when we are using space character. But space is must in some of the declarations, because after you use space, it will call some of the functions and instructions that should be understood by the Verilog HDL. That's the reason when we write entire Verilog HDL in some EDA, right? These functions, assign, reg, wires, input, outputs, all these terminologies will be turned into purple or pink. So that are already existing in the Verilog HDL online compilers or any compilers. So these are understood in a different way. Those are not our variables or registers. So yeah, I'll show it in the next slides. And coming to the other attribute, we usually write HDL understanding, HDL equations or understanding of the architecture using these operators, and we construct the Boolean equations or some logic functionalities in the process by using and, or, not, XOR operations and all the arithmetic operations. I'll show you the operators in detail as well. Let us go to the next topic. So our next topic is data types, Verilog HDL data types. So what are data types? Now here comes a big question. In the Verilog HDL, you want to store some data or store some values of integers, numbers counting from 1 to 10 or 1 to 100. You want to operate those input values. For example, if your input is a binary value 1001, as we have discussed, how do you keep this binary data into the input port, or how do you make it transmit from the input port to the internal function processing, you might need a medium. So that type of medium in terms of physical or in terms of logical, there should be some via media which can be carrying that information to the processing end. So that at the input or out input will be called as data type. So data types are nothing but integers or strings which are variables. So these variables are responsible for our data processing for shorter period. So we represent any input value into these variables. So data types are elements to represent the characters used in the hardware description language. As I said, some of the data types are integers and strings. Like integers are numbers and values, okay, and strings, it is again characters. For example, if you are giving a data as name should be taken in terms of strings. Mostly we can go with the integer because it's a HDL, right? But strings we do use, and in the next sessions we will be discussing about these data types and usage of these data types as well. Now in this class we will be discussing about integer data types. And now going to the logical values represented everywhere in the HDL language, we are talking about hardware description, right? So entire hardware description in terms of machine, in terms of processor or chip, it can understand binary values and also two set of values which are don't cares and don't cares and high impedance. Z is nothing but high impedance. When it is called high impedance, if one of the port has 1 as input, another port has 0 as the input data, and one port has no value, don't care, you might not be using that port, you can say don't care, and then whatever the value comes, it is not affecting the logic function and you are not using this port anywhere, so it can be don't care. So the other kind of thing is leaving the port in the open circuit. For example, you have a 4 by 1 mux and all these three ports are A, B and C and D. So it is 1, it is 0, and whatever value 1 or 0, it doesn't care, you are not selecting this C port, and D, now it is open. So now it is open, it is don't care, in this way. So simple analogy you will understand in the next slides. So where X is don't care and Z is high impedance. I have written here to give you as a note. Please make a note of these things. And then Verilog HDL is case sensitive and time specific. You need to mention time in this way. When you are mentioning clock, right? You need to mention time. For example, in the previous lecture, we have used $time in the EDA online playground for $time to show when this input has been printed, when this output has been printed, and when in the counter example. So we have seen example 1010 nanoseconds, and you can see 15 here somewhere. 1010 nanoseconds, or we have seen 510 nanoseconds. At the 500, after 500 nanoseconds, the clock has been stopped, and you can see 510 nanoseconds and 7. These are not same. It is $time and it is the counter output. Likewise, we have seen in the following way. So we need to specify $time in this way. Remember these as it is. To mention time, okay, we need to mention $time. There are some other elements to be remembered. So this is all about how do we remember. See, even if we are talking in English or any other language, it has some grammar in it. So there has been some rules that you need to follow while you're talking or while you're communicating with other persons. So in the same way, when we are writing HDL language or when we are developing some programming language, those languages when we develop have some set of rules, attributes and data types, keywords, all other elements that we use to construct a language. So and also we should follow a syntax, which is the rules kind of thing to write any line of code. So then and only then the language or the script that you have written will be understood by the processor or any other machine, even through the laptop. So set of commands. Hence, registers are declared with the following syntax: reg size of the bit, what size of the register. Here register is not only the memory element, but any device that we are describing in this output wires. I mean, outputs are also called as registers and inputs are always called as wires. So wires are nothing but interconnects. For example, if you have mux and if you have an OR gate. If you have OR gate, so the interconnect is nothing but wire. And registers, whatever the output you get from this mux or this wire can also be called as register in terms of OR gate. But this wire, let us say A can be output register in terms of OR gate, but A can be input wire in terms of multiplexer. When you are writing multiplexer code, right, A can be written as wire. Understand, guys? I'll be explaining in detail. So you have mux and you have OR gate and you have connected one wire to this, the output. So you have A as input and B as output and C as output for the OR, and some other Z as the output for multiplexer. Now here understand, now we are writing module OR gate and what we are declaring? We are declaring input and output ports, right? Input we declare as A and B, but we need to declare wires. What are wires? What are registers? Outputs are registers and inputs are wires. So what is the output here? C. We need to write output, but I am writing shortcuts. Output is C. Now wires are A and B. What is register? C. This is how we declare. Now we can declare register as, okay, C 4-bit register, 4-bit output. So C, or we can declare 5-bit also. We can declare 8-bit like 7. Anything. You have to mention the size of the wire if you are seeing any carry in the operations. I'll explain in a bit in the arithmetic operators. So registers. So in this way, but what is the input for mux? Input is C. When you are writing module mux, input is C. So that is how you should be so specific between every other logic cell. Nowadays EDA tools have automated our entire flow, and those have generated Verilog HDL scripts on their own and for all the modules depending on it. So hence if you write OR gate and input as C, now the machine will understand, okay, now there is one logic cell that is OR gate, and from that OR gate we are taking output C, and that C is input here. Hence, the connection will be happening from OR gate to multiplexer. Understood, guys? OR gate to multiplexer happens. So you need to mention. And now what is the output here? It is Z. So what we are doing in HDL language, we are making a script to develop each logic cell and then connecting those logic cells if they are connected. If we want them to be connected in the architecture, we are connecting them by looking at these kind of rules and syntax. Why don't we keep register C in the multiplexer here itself? No, this wire, this net C, this net here, after output, after logic cell, if you see any net connected between other cell, the net is called register for the output of this module. But in the same way, this is the input for the next cell. So for this module, for this cell, I mean module is nothing but cell, the device. Multiplexer is a module. So in this multiplexer, what is the input? C. And for the OR gate, what is the output? C. Data is same. Whatever data you collect here, it is sent to this part. Got it, guys? So I'll show you in the next example as well. Let us go to the other data types. So what are the major data types we have in Verilog HDL? We have vectors, like normal vectors. You can see reg 8-bit A can be one element, simple element that can be output, or that can be a storage element. You don't know that. So A can be output or storage element or any other element that we are just mentioning as a wire or any other data collecting output somewhere in the registers, as like database are declared. So whenever we say data bus means for data bus we should specify the size of the data bus. Data bus is nothing but a wire goes with 8 bits. It can transmit 8 bits at a time. So 8 bits means 1 2 3 4 5 6 7 8. So here we have one 8-bit bus. It can carry only 8 bits long. It can't carry 16 bit. So when 16 bits of data comes, 1 0 0 0 1 1 0 1 1 1 0. If you have 16 bits long, you will only collect 8 of it. So only 8-bit data will be transmitted and another 16 bits will be lost. Hence, if you specify it as a 16-bit 15:0, then you can transfer 16 bits of data or 8 bits of data or even 4 bits of data. So hence all the data bus are specified with same length. If you are operating at 32-bit, entire processor should operate at 32-bit. Hence all the registers will be mentioned as 31 0 and A. That should be the declaration. And in the same way, how do we mention arrays? When we declare arrays in the function, right, we have to declare reg A after size of the array. This is the size of the array. Size of the array will be declared in the next, if this is the array, you can mention how much size. For example, here it is 3 4 5 6 and 8. 1 2 3 4 5 6 7 8. So now it is 8-bit array. In the same way, now if we are looking at 9, it is 9-bit, 10, it is 9 and it is 10-bit array now. So 0 1 2 3 4 5, 6, 7, 8, 9. So in the same way, so arrays will be storing the bit by bit. So each column has one bit of memory, whether it might be 1 or 0 or 0 or 1, 1, 1 or 0. Any type of data, any bit can be present in one array, one position of the array. So in this way you can see the array. And how do we make the memory is a matrix. Like, imagine a square box where this is a square box of memory. You need to declare how many number of arrays you need to have in this thing. See, if you make it happen, right? So this many number of arrays you should have. This many number of arrays you should be having like this. And you should also mention each array how many bits of data it should acquire. So I'll show it in the next diagram. So memories are matrix of storing data. 1, 0, 1, 0, 0, 1, 1, 1, 1, 0. So it can store elements in this way. So the data is processed in this way. So entire data will be pushed forward to the next cell or in the before cell. So this can be of lookup table or this can be of SRAM as well, but these are to be represented in this way. In the same way, remember this syntax. 7:0 is nothing but size of the array. Here you can mention how many elements, number of bits per array. I mean, if this is the bit, it can store in the array. So it should store 8 of them, 4 and 4. This is 1. Okay. So all this is 4 and this is 4. And now this is the number of arrays you should be. So arrays you should declare, okay, these many arrays. Now you imagine size of the array is, you can mention as, this is the size of the array. So we have declared 0 to 9, that is 10. Same way you can mention 10. And what is the size of the each array, number of bits, you can declare as this one. You should have 8 bits per each array. 8 bits per each array. I'll show it in the next window. Understand, guys, memory is a matrix. So this way you can mention. So this 7 should be the mentioning like vectors. So this declares how many should be available in the in a row of matrix. So in the element, this element is of size, or this can, if this is a wire, right, this is a wire for 8 bit. As I told, 8 bits can transfer in this way. Like this way, it goes in this way. For example, data goes in this way. Okay, so data goes in this way. 0, 1, this goes in way, this way, size. So now what we are declaring, this one will be represented in this way, and this is the size of the entire memory, and how many arrays you should be having from here to here. Understood, guys? Keep in mind, every time you write a memory, you should mention, okay, we should have, write this one first, we should have this many arrays, so this much of size. For example, if you are taking 1 kilobyte for each row of data, you are taking 10 KB. 10 KB. So if this entire data is 1 KB, Now this entire 10 arrays will be as 10 KB of memory. Understood, guys? So in this way you can mention memory declaration, and I have mentioned as 8 bit memory, 8 bit, and I can also see as 4 bit. Here register size, this entire array can be of register. That's what we are declaring, register array. And now array, and okay, and now this is the 10 registers. Here again register is arrays. I just have declared another example like 8 bit. Now we have 4 bit. So arrays are registers here, just to make you understand. Go through this again. Then as we have discussed macros in the script, Verilog HDL have some specific functions to use them for the entire program. For example, if we are writing hash include, tick include. Tick is a symbol above the tab in your keyboard. Just check it there. Tick include syntax and tick include half adder dot v. What it does is it takes all the information, all the Verilog HDL file, and it will add all the registers or all the inputs, outputs, modules that you have used in the half adder into your existing Verilog HDL file that we will be using. You will be understanding these elements. Just remember as it is, and while we are developing the program, you can see. So now tick timescale is a syntax, and tick timescale, the syntax is reference time by precision time unit. We have mentioned tick timescale. Tick timescale, did you remember 1 nanosecond by 1 picosecond? This has to be mentioned because whenever we use program hash 10 script, if we use hash 10 or hash 100 or hash 500, it shows that this is 500 nanoseconds or 10 nanoseconds or 100 nanoseconds. How is this understood by the machine or the processor or the HDL language script? That we have declared in the beginning of the code as tick timescale 1 nanosecond by 1 picosecond. So we need to mention those kind of things and define syntax. Tick define, I am mentioning syntax to understand if you are using this kind of element, right? You need to mention in this kind of syntax. So tick define size 32. It says entire function, you entire Verilog HDL, you maintain the size of the bits as 32. So these are defined and these are executed at the time of HDL compilation. So compilation is like after you develop the script, you are giving to the compiler for executing it, for checking all the errors and all, and make it functional on the hardware architecture. Now Verilog HDL development. So till now we have understood all the attributes, elements present in the HDL that we see while we are developing the HDL language, and from now on we will be developing the HDL language in gate level and data flow model by using all the elements. See, now we have seen output, input declaration, 2x1 multiplexer, and what this code we have already written from the Boolean equation and also from the gate level model. So we can develop Verilog HDL by focusing on these major components. Every time I write parts, right? Part 1, part 2, part 3, all these parts of the Verilog HDL code, you should be remembering this flow. What is the part 1? We declare timescale. Part 2, we declare module. Part 3, output, input, wires and registers. Part 4, process. Part 5, end module. So I need to write it. So part 1, it is tick time scale. As I have mentioned this tick time scale, this is part 1. And part 2, it is module. And part 3 is declaring output and input wires. Part 4, it is and OR gate. So part 5, it is AND module. Means part 4 is dealing with process. You can mention with and OR gates or XOR and OR gates, and you can also start writing begin some loops, begin if function and end the process, begin process. And also there is one another mentioning always. Always is the continuity of the values. If the values change, then the entire operation changes. The code executes again when the always function values have changed. Always follow input wires. And yeah, that's one thing. And we can also see top down and bottom up approach in the end module. So top down and bottom up. What is top down and bottom up, guys? So till one example I can show you. I'll be stopping at this point because it will be overwhelming if I proceed further. But yeah, top down approach is nothing but, imagine you have a block of elements, one block. Let us take one block which has IO block and CLB. This is CLB, and also it is connected to switching matrix. So it is connected here. What we are developing top down or bottom up, what is the major difference? See, if you have a block design and inside if you have AND gate, and inside and AND gate, and other AND gate, let us say, and some OR gate, all these elements are interconnected. Okay, all these elements are interconnected, and if these are making you a register again, some kind of register, and in this register, right, you also have flip-flops connected, and you also have multiplexers, bunch of multiplexers, not one multiplexer. I am telling some n number of multiplexers and m number of blocks, I mean flip-flops. This can be mux. So all these elements, AND gate, OR gate, AND gate, OR gate, and flip-flops and multiplexers, if all these elements are inside this block, how will you write a code based on the elements? You shouldn't be confusing. Then we have made an approach, top down and bottom up approach is like, first you declare smaller elements, and after declaring smaller elements like OR gate, AND gate, after you have written Verilog HDL codes for each logic cell, then you are writing the Verilog HDL for this entire block of the module. So you are coming from the internal elements to the external top level design. That is nothing but bottom up approach. Bottom means when you deep dive inside a block, you will be seeing logic cells. If you write module codes for the logic cells and you take care of input and output wires and how they are connected, take this information of the internal elements and come to the top level design where some other elements like flip-flops or multiplexers are connected. Write the module codes for HDL codes for each of the cell and connect these input and output wires according to those multiplexers. Like one Y is output for this AND gate, that can be an input for flip-flop. So if you are writing a top level HDL code for the flip-flop, then the output here for this AND gate should be like input for flip-flop. As I have mentioned earlier in the class, it is C. For OR gate, it is output, and in the multiplexer, it is input. In the same way, Y is output for AND gate and input for flip-flop. Can be an input for multiplexer as well. We don't know. We don't know the connection. But what I am talking is, after you design the internal blocks, and when you come to the top level for top level design, then you can see this is the bottom up approach. And if you develop the higher elements, the top level elements, and when you go to the internal of this internal of those higher elements, for example, you are designing mux now. If you are designing mux now, let us say this can be mux, and inside mux you have AND and OR gates. Let us assume inside mux you will be having AND and OR gates. So for that, what you need to do is first write Verilog HDL module for this, and then write the internal script. Got it? So that is top-down approach. This is simple, guys. You will be understanding sooner. And yeah, note, in this development of HDL code, one should be aware and so sure about inputs, outputs, wires and registers declaration, as I have mentioned. So example, module top level ZYX and input XY, output Z and wire XY. Now if you can see another AND gate, some top level design, it is top down approach. Then we can see the input is A and B and output is XY. Got it, guys? So you can see the changes, input X and Y, output X. So that is how the top down approach works. For AND module, inputs are X, A and X, but output is X. This output is connected to the top level design as the input. Understood, guys? So this is how you will be developing. Don't worry, as this is the beginning of the Verilog HDL construction, we will be discussing in detail in the next session as well. So that's it, guys. And one last topic for this day, you can also think of ports, where you need to declare ports. As we are declaring input and output ports, these can be like all inputs are wires. Remember, all in-out ports are also wires. We also have in-out ports, which is for data transmission, for both side transmissions for the ports, and but all the output ports are declared as registers. Remember, output port for that specific logic cell. Okay, these ports are medium. These ports are the medium and responsible for the connection to the external elements with the internal cells of the chip. Like these ports are the communication bridging between internal logic cells of operation, like for example addition operation, and that addition operation will give the output, and output will be displayed on the LCD. How these are interconnected? Through these ports, we usually call as pads as well. So IO blocks are also designed at the ports stage. So in the FPGA development, IO ports are also designed. So you can see this is how ports look like in the design. So in out, wire and net, in out, input, wire or net, and output, register or net. So you need to think of, if this is a register, you have input port, in out port, output port as well for a register, or if you are designing a module. Okay, again module can be a register again, you never know, but reg is a common term used for all the elements in the HDL language. So this is it, guys. Thank you for attending today's session. We will be discussing more about all other Verilog HDL codes using data types and using arithmetic operators. We develop the examples. Stay tuned to this session as well. We will be continuing with the next lecture. So if you have any questions, just let us know. We will be discussing in detail. So thank you, guys.